Perhaps you've had this experience. You pick up a hand calculator and you go to do some fairly simple trigonometry calculation. Let's take, for example, the tangent of 45 degrees. You type in tangent 45 and you expect the answer to be 1. That's a very common even calculation to do. So we press enter and we get, oh no, 1.61977. What went wrong? And then you think, well, maybe you'll try another simple special angle for a trigonometry function and see how that turns out, like the sine of 30, which we expect to be 1/2. And you enter that and, oh, I'm getting all kinds of wrong answers. What's going on here? And then you realize in the corner of the calculator's display, it says rad instead of DEG for degree. And you think, oh, I'm in the wrong unit of angle. Well, that's true. So you can go over here and switch to mode and switch this to degrees. When you do that, now you can redo those calculations and they should turn out the way you expect. So tangent of 45 degrees gives you a value of 1, and the sine of 30 gives you a value of 1/2. Those special angles that we're used to calculating trig functions all work out. But it begs the question, why even have radians or rads? What's the point of that? Why not degrees? Degrees seem so simple. You take a full circle and you divide it into 360 equal parts. Each one of them we call a degree. So what exactly is a radian or a rad? So if we take a look at a circle, any sort of circular object, if it's a perfect circle, if we measure the radius of that object, the distance from the center to the periphery of the circle, and then imagine taking that radius length and laying it out along the outer edge of the circle. It's not going to reach all the way around, of course, it's too short for that, but the degree to which it does reach, if you mark that as being an angle, the angle formed, the sector of that circle formed by the radius length laid around the edge is 1 radian. So that is fundamentally a natural way of measuring angles because it is based on the actual geometry of the circle. When you consider degrees, which is rather arbitrary, taking a circle and dividing it up into 360 equal parts, well, why 360? There's no natural reason, no logical reason why you might want to divide a circle into 360 pieces versus 300 or 100 or any other number. In fact, the French, during the French Revolution, actually had an idea called the grad, and we see that in some calculators here. And in the unit of grad for angle measurement, there are exactly 400 of them to one full circle. So that's just as arbitrary as 360. So when you look at the way the radian is defined, it's literally defined based on the geometry of the circle itself. There's really nothing arbitrary to it. Now, it may seem strange because instead of having a whole number of angular units to measure out one circle, you have this irrational number. Because if you look at the length of a radius and the length of the circumference around a circle, there are exactly 2 pi radius lengths making up one circumference. And so there are 2 pi radians in a full circle. So if I were to write this out here, a full circle equals 360 degrees equals 400 grads. Again, those are just arbitrary units of measurement for angle, or it's equal to 2 pi radians. Now that may seem very strange because again, pi is an irrational number. It's not a nice whole number like 360 or 400. And so at first it may seem weird. It may seem strange to try to measure angles of a circle in that manner. But there's actually good reason for it. And it really comes down to this. It is a natural way of expressing the angular measurement since it is based on the geometry of the circle itself and not an arbitrary division based on some numbers that someone just came up with. So let's talk about some applications and see exactly how and why this works. So if we take a look at rotational motion and compare that with linear motion, when you're calculating quantities in physics type problems or engineering type problems, if you're dealing with linear quantities, force is typically measured in newtons in the metric system. Linear displacement is in meters. Velocity is in meters per second. acceleration is meters per second or meters per second squared, and mass, of course, is in kilograms. Those are the standard base units of the metric system we're used to using and working with. And you've seen equations like this: F equals ma, basically Newton's second law of motion. The amount of force we apply to a mass is proportional to the acceleration. So if we look at that, those are very standard equations. You're all used to working with those if you've taken a physics course before or done any sort of engineering problems involving kinetics or motion. If you take a look at the rotational equivalent, you find out that if you measure the rotational equivalent of force, which is called torque, in Newton meters, and you measure the moment of inertia, which is the rotational equivalent of mass, in kilogram meter squared, the only way the formula works out as nicely and neatly as the linear version is if you express all the angles in radians, not in degrees, not in grads, but in radians. And again, the reason for that is that fundamentally the radian is a natural way of measuring angular quantities. So the linear measure of displacement is in meters, straight line motion. The angular equivalent is in radians. It's how many angular units we've turned an object, we've rotated an object. If linear velocity is measured in meters per second, angular velocity is in radians per second. If linear acceleration is in meters per second squared, then angular acceleration is in radians per second squared. And if you do that and you analyze dimensionally all the units that go into it, the equations for rotational motion are just as elegant and simple as the equations for linear motion. So to make this a clearer contrast, we could ask the question, what would things look like if we tried to use degrees? How would this formula change if we wanted to use degrees to measure the angle rather than radians? Well, we know that one full circle is 360 degrees. We also know that one full circle is 2 pi radians. So if we're going to use degrees as the unit of measurement for our, in this case, angular acceleration, we would have to include a conversion factor to convert from degrees into radians so that the rest of the units would work well together. So our equation would look something like this. The amount of torque that we apply to a rotating object is equal to its moment of inertia. And then instead of alpha here for angular acceleration in radians per second squared, we would have to have alpha in degrees per second squared. But when you enter degrees, you have to convert that mathematically into radians. And so what you'd end up doing is including this conversion factor, 2 pi over 360 times alpha. Your equation would have this rather ugly, and some might argue unnecessary, conversion factor in it just to make the units work properly, just to make the units play well with each other. That's kind of ugly. And if you're doing a lot of calculations, it's additional room for error. It's additional opportunity to make mistakes, to forget the conversion, to do the conversion wrong, etc. Whereas the canonical form of the equation here, using angular units in radians or radians per second or radians per second squared, is just as elegant as the linear version of that. So that's fundamentally why radians exist in engineering type problems. You could explore it mathematically as well, how you can derive, for example, trigonometric functions from an infinite series, which is something that Leonard Euler did. And you take a look at how you can derive the sine and the cosine functions from exponential functions of E, Euler's constant. You find that, once again, the only way that math works out is if the angle is expressed in radians. Why? Because, again, the radian is a natural measure of angle. The degree is arbitrary. So even if we consider degrees to be friendlier, more familiar to us, mathematically, they're strange. The radian is the natural unit. And so in some areas of science and engineering, and especially mathematics, we find that the radian is the preferred method of angular measurement.